let's get started the next video. In the previous video, you will understand the, how importance of thinking about the heat and temperature change of the chemical reactions. So in this chapter, I will talk about the heat and temperature change of the system. The first, we need to discuss about the change of the internal energy. The internal energy was expressed as large U, as shown here. The internal energy is the energy, all types of energies are included. Then the internal energy is the universe of the energy. Then we used large U as shown here. What is all types of energies? The kinetic energy, bond energy, and other type of energy, all energy are included in the internal energy of the system. This is the box. Within the box, there are many molecules. All molecules are moving, having the kinetic energy, and all molecules have bonds. That means the bonding energy are included. Okay, and you can change the internal energy by adding the pressure or heat like this. Can you understand this in a cartoon? This is your hand. Your hand can push the box to add the pressure. And also you can use the heat unit to change the temperature of this system. By adding heat, also you can change the internal energy of this system. The change of internal energy can express by the Q, large Q plus large W. Large Q means the heat, this one, and large W means the work, like pressure, okay? And work done to the system expressed the plus W, okay? Work done by the system shows the minus W. This is the, just the direction of the work. So you do not need to think seriously. Sometimes, plus and minus will be changed to the opposite. But at this time, I will use plus means the work done to the system, and minus means the work done by the system. And what is work actually? I write here the pressure can act as a work to the system. But the pressure, just pressure is not the work. Work is pressure times the difference of the volume, okay? If you can change the volume, that could be the work. So I would like to explain this part. Maybe all of you know the work equal force times distance, okay? If you add the force and move some, material to the other part with some distance, that is the work, okay? if you use the Kuroneko Yamato Takyubin, in that case the your some material come from your country, that is a big work. That material coming from your country a large distance from your country, so the distance is here, and always that package coming from your country, always the package push to Japan from your country is a big force need, so that is a big work. And in another point of view, maybe you understand the pressure equal force over area. Okay, so if you use these two equations, you can understand the work equal P delta V. Here you can see the cylinder here, and the some pressure act as the cylinder, act into the cylinder, and distance x here. So the force pressure times area. Okay, pressure times area means the force, and area times distance means the volume. So pressure times the difference of volume means the work in force times distance. Okay, so work equal pressure times the difference of volume. This is very important idea. Then we can calculate the change of internal energy by the use of the change of volume and pressure. Okay, this is one of the good example how to calculate the delta U. I mean the change of internal energy. You can see the balloon here with the volume V1. This is also another balloon that contains the argon gas with the volume 2. Okay, the pressure, external pressure, is always the same, 1.01 times 10 to the 5 Pascal. The volume 1 is 2.30 liter, and volume 2 is 2.05 liter. So this balloon shrinking and transfers 485 joule to surrounding. This is heat. So do you remember the delta U can calculate by Q plus W, but in this case, the work done by the system, I mean the work done to the system, work done by the system means minus, okay? So here you can see the Q minus W because work done by the system. So W can transform to the P delta V. So you can express the difference of the internal energy equal Q minus P delta V. Then you can easily calculate the change of the internal energy by this equation and these values. Okay, the Q equal minus 485 joule. Okay, 485 joule to surrounding. To surrounding means the minus. Okay, and minus work can estimate by the pressure times the change of volume. And importantly, sometimes the student confusing the units. Okay, the converting the same unit. This is very important idea for the physics. Joule minus Pascal times liter, but joule can transform to this unit. Okay, and Pascal can transform to this unit, and liter is liter. But Pascal is this one, so you can remove the liter from the units. And here you can see here is the meter cubic, and here is the meter. So you can remove 1 meter here, and as you can see, the unit are all the unit are same as joule. So internal energy, unit of the internal energy change should be the joule. Okay, and here is the equation, and here is the answer. You need to calculate by the use of the calculator. Okay, you can use calculator like this, right? Okay, and you can check the answer by the use of the calculator. Okay, and this is very important. You can calculate the internal energy of the system after changing the internal energy by adding heat or pressure or work something. Okay, and this is the another important point of the internal energy. Heat versus temperature. You add heat to the system. Sometimes temperature change are big, you can observe the big temperature change. And sometimes you cannot observe the big temperature change by the same heat. This is very important. This depends on the specific heat of the material. So this is very important equation. Q equal mc delta T. Delta T is the temperature change. Q is the heat. M is the mass and C is specific heat. Some guy says that this equation can easily memorized by the MCAT. Here you can see the MCAT. This is very cute. So Q equal MCAT. How can you use this equation? Please try to think about the how much heat do we need to apply to change the 20 degrees C water, 2 kilogram water, to the 50 degrees C 2 kilogram water. The specific heat of the water is 4,186 joule per kilogram dot degree C. Then you can calculate how much heat do we need to apply to this change of water, Q equal 2 kilogram M, 4186 C, and delta T here, 50 degrees C minus 20 degrees C. You need to add 251,160 joule heat to change this, water temperature. If you understand this equation, I mean the MCCAT, you can calculate the temperature of the system after mixing two materials. Okay? So this is the practice. Calculate the temperature of the system after mixing the copper 90 degrees C, the specific heat constant of the copper is 387 joule per kilogram degree C. Okay? And here you can see the water, 2 kilogram, 20 degrees C, and the specific heat is 4,186 joule per kilogram degree C. If you mix these two systems, I mean this copper of which temperature is 90 degrees C, put into this system water in the bucket or something, So how much temperature can you observe after mixing the copper and water system? The important idea is, note heat loss, Q equals 0. You can, set the final temperature because, the temperature should be the, same after mixing, the water temperature and copper temperature go to the same temperature. And after changing the temperature, the Q, total Q, should be the 0. I mean, the, copper change to the lower temperature, water change to the higher temperature. But, the temperature, final temperature should be the same. Copper temperature and water temperature should be the same, okay? And important thing is, heat total should be the Q should be the 0. So you can make the equation of the transformation of the system by the use of the internal energy and Q equal MC cat. This is the assignment today, so you will submit the answer of this practice to me via Moodle, okay? So the next week, I will discuss the answer of this practice and then move to the, some discussion about the enthalpy, because internal energy is not appropriate method to discuss about the energy of the system. Maybe you can understand after the calculation of this, practice. Let's call it a day, okay? And see you next week.